Okay, welcome to lecture number 16. Here we're going to continue our discussion of matter and heat. I'll say part two. And we're going to discuss a little bit right now about fluids. Okay, we know what a solid is. What is a fluid? Fluids, there's technical definitions, but I'm going to be a bit cavalier here. So listen to me. Suppose you have a solid. What does a solid mean? A solid, in very simple words, a solid we can consider as something where if you take any two atoms or any two molecules or any two particles in your system, the distance between those two particles remain fixed, does not change. In a fluid, if you pick any two molecules or any two atoms or any 2 points in the fluid, they're constantly moving. By this definition, certainly liquids are fluids. So I'm going to put here, liquids are fluids. But we also see that gases are also fluids. All gases are fluids. All liquids are fluids. Are all fluids liquids? No. Are all fluids gases? No. In a gas, the distance between any two particles is constantly moving. In a liquid, the distance between any 2 points constantly changing. Okay? So this is our simplistic definition of what a liquid is, what a fluid is. Now, just a quick reminder when we talk about density, mass density is the mass of something over the volume. So it would be grams per centimeter cubed or kilograms over meter cubed. Any mass divided by any volume. Milliliter is a cubic centimeter. Okay, so any of those units work. But I'm not going to talk about that. What I want to talk about is what you're feeling right now, which is pressure. So in society, we have pressure, many pressures as students, as parents, as workers, whatever. In physics, we're going to define very specifically what pressure is. So I'm going to define it, and then we're going to play with it, and I'm going to show you that you still are not comfortable with units, okay? Now, pressure, P, capital P. What was small p? Small p, remember, was momentum, mv. Pressure is going to be defined as the force applied to an area divided by the area to which it is applied, to which it being the force is applied. Okay? It's force over area. So let's look. P equals force divided by area. Now in our units, force, remember, was newtons. Kilogram meters per second squared. Area, length times width, to be consistent with newtons. Remember newtons, kilogram meters per second squared. So area is going to have meters squared. Newtons per meter squared has a name. The name of pressure unit is called a Pascal. So Pascal is a unit of pressure. Okay, that's one unit of pressure. So I'm going to talk about pressure and different units and things like that. Okay? Does anyone know what units pressure is measured in the United States or in Brooklyn? Okay? Probably not. Well, let's talk. Pressure is a force over an area. What do we measure force in? Well, we said newtons, but we don't use newtons in the United States, right? In general. What do we use? Well, what is a force? Well, we said your weight is a force. Weight is measured in newtons. In this country, weight is pounds. So we measure force in pounds. What is a nice unit to measure area? Well, inches. Inches squared. So in this country, we're going to measure pressure. Let's look at the units. We just said pascals. I'm telling you now, in this country, we measure it in pounds per square inch, usually written PSI. So if you fill up your bicycle tire, it's measured in PSI, 30 PSI or what have you. Okay, there's another unit, it's very nice. It's called 1 atmosphere or just atmospheres. We'll just say atmospheres, ATM. I will tell you what that is. Okay, then there's another unit that measures mm of Hg. Wow, what is that? mm of Hg. mm is millimeters of, does anybody know what element Hg is? This is mercury. Millimeters of mercury. Okay? And the instrument used, and I'll tell you how that works, for measuring pressure is called a barometer. Barometer. Okay, let's do this quickly. A barometer is a U-tube, not a YouTube, a U-tube. It's a tube shaped like a U. Okay, so I'm going to draw a U-tube like this. Ooh, supposed to be symmetric. I apologize. What a beautiful U-tube. Okay, inside this U-tube, we have a fluid. Usually that fluid is Hg, mercury, because it's very dense. This side, doesn't matter which side, is open to the atmosphere. So air pressure pushes down. Now, air pressure pushes down. If this side goes down, this side goes up, except this end is closed to the atmosphere. And here, in this area, we have a vacuum. How do you make a vacuum? Just take the liquid, pour it all the way in there, and then pour it back, and there'll be no air there. So this side, we have open to the atmosphere. This side, we have a vacuum. Here, we have a measuring rod or something to measure the height. As the pressure increases in the atmosphere, this side goes down, this side goes up. And so we can read how high or how low the pressure is in mm of Hg, millimeters of mercury. Okay? Now, let me go back and talk about pressure, air pressure. Okay? Now, again, pressure is force divided by area. Okay, so I want you to watch. Okay, use your imagination. Suppose this is us on Mother Earth. There we are. Okay, that'll be me. Nice nose. Okay? Air is all around us. Does anybody know what air is made of? The air we breathe. Okay? It's approximately 78% nitrogen. N2, nitrogen molecule. About 21% oxygen. O2. And about 1% other stuff. Methane, carbon dioxide, and other things. Okay? So it's primarily made of nitrogen and oxygen. So we have air on top of us, all these air molecules. Suppose we're at sea level or at sea level. All this atmosphere is on top of us, which means all these nitrogen molecules and oxygen molecules, they have a weight. So they have a force and they're applying it to our body. At sea level, we call this atmospheric pressure. Okay? At sea level, we're going to talk about atmospheric pressure. Okay? I'm going to come over here, and I'm going to tell you some units. for atmospheric pressure at sea level? Well, our first unit, P atmosphere, the first unit we talked about were newtons per meter squared, which was a Pascal. Here's atmospheric pressure in pascals, 1.01 times 10 to the fifth pascals. That's a very big number. What a pain in the butt. Okay. It's also equal to 1 atm. So you can measure pressure in atmospheres. That's very, very easy. Millimeters of mercury, 760 mm of Hg, usually considered atmospheric pressure. And pounds per square inch, I believe it's 14.7 pounds per square inch. That's almost 15 pounds per square inch. I want to talk about this number because we can kind of understand this number. We don't know what the hell a Pascal is or atmosphere or millimeter of mercury, but pounds per square inch we can physically get a feel for. Okay, so I want to talk about that right now. Let's round this off to 15 pounds per square inch. What does that mean? It means if I'm standing at sea level, every square inch of my body is being pushed in by the atmosphere with 15 pounds of pressure. Every square inch of my body. 50. Now, if you're weak like me, no muscles, okay? If you take 15 pounds, pretty heavy. 15 pounds is pretty heavy. Imagine 15 pounds pushing every square inch, your eyes, your nose, your ears, your belly buttons, every part of your body, every square inch. 15 pounds of pushing in. The question is, how come we're not crushed like a tin can, just crushed? So my question is, if there's 15 pounds per square inch of atmospheric pressure at sea level pushing on your body, what is your body's pressure? Well, since we're not being crushed, common sense tells us that the pressure being pushed in must equal the pressure out. So your body pressure is approximately 14.7 pounds per square meter, per square inch, or 15 pounds per square inch approximately. So that's your body pressure. Okay? Now, remember we said here we are at sea level. Okay? We have all this atmosphere on top of us. What happens if you go up in the atmosphere and you go in an airplane? There's my airplane. Okay? What happens as you go up in the air? Well, if you go high up, or if you climb a mountain, if you go 1 mile high, like in Denver, you're 1 mile high. Notice the higher up you go, the less atmosphere is on top of you. The less atmosphere on top of you means the less pressure. So the higher up you go, the less pressure there is. That's why when you go in an airplane, they try to pressurize the cabin to 14.7, your body pressure. Sometimes they don't do it adequately enough, and your ears then would pop which way when you go up? Do you know? Well, you're still putting out 14.7. The higher up you go, the less that the pressure is, so your ears would pop outward. They pop outward. Okay? If you dove underwater, deep underwater, as you go deeper and deeper in the water, you have more water on top of you, you have greater pressure, your body's still putting out 14.7 pounds per square inch. Now, the water pressure exceeds 14.7 pounds per square inch, and what happens is your ears pop in. And if you go too deep, you pop in, you get crushed. Okay? If you went to outer space, where there's no atmosphere, what would happen? Well, forgetting temperatures, if your suit opened up, what would happen to you? The answer is you'd open up because your body's still pushing out at 14.7 pounds per square inch. If there's no pressure inward because you're in a vacuum in space, your eyes will pop out and would not be pretty. Okay? So, atmospheric pressure, 14.7. What about water boiling? Well, we'll talk about water boiling later on, but essentially when you heat water, you're adding energy to the water. The water wants to escape. It wants to escape even though there's air pressure. If you go very high up, like in Denver, there's less air pressure, means the water can escape more easily, which means you need a lower temperature to boil water. So at sea level, if water boils at 100 degrees Celsius, in Denver, perhaps it would boil at 97 degrees Celsius because there's less pressure pushing down. The water can escape more easily, and so you don't need as high a temperature. Okay? Fantastic. Now I want to give you a problem, a math problem with this, and see how you can do. This involves unit conversion. Oh, you thought we got away from unit conversion, but we haven't. Okay, let me give a little spritz here. 1 second. Okay. So I want you to work on this problem because this is a good problem. And it's a good review for your units. The equation's easy. Pressure is just force over area. So we're going to write this. P equals F over A. Okay? Remember, that's going to be newtons per meter squared. Okay, and that's a Pascal. So now for a problem, okay? What is the pressure on an area of 20 millimeters squared? It's my area, very small, 20 millimeters. What is the pressure on an area of 20 by a force of, okay, I'll make this up, 80 N. All right. So what is the pressure on an area of 20 millimeters squared by a force of 80 N? Now, what is N? Okay. Little n is nano. Capital N is newtons. So I'm telling you the force is equal to 80 N, which is 80 times 10 to the, what's nano? You remember? -9 newtons. The area is 20 millimeters squared. Now remember, to get the answer in pascals, I need meters squared, not millimeters squared. So we got to convert millimeters. Let's do it together. Let's see what we can get. Remember our line. I'll do it right here. 0 plus 3 is kilo, -2, -3, -6, -9. Nano, micro, milli, centi, kilo. So we have 20 millimeters squared. So how do we convert? Millimeters, here's meter. This is meter. This is millimeter. So so 1 millimeter is how many meters? Well, this is bigger. So remember, bigger is negative, right? And there's 3 steps. So 1 millimeter is 1,000th of a meter. 1 millimeter squared is 1 millimeter times 1 millimeter, which is 10 to the -3 meters times 10 to the -3 meters. So 1 millimeter squared is 10 to the -6 meters squared. We're not done yet. I want 20. Well, we don't need to do that. So watch this. I now plug these numbers into my formula. So watch. Pressure is F over A. It's 80 times 10 to the -9 newtons. That's good. Divided by 20 millimeters squared. But a millimeter squared is 10 to the -6 meters squared. Twenty into 80 is 4 times 10. Look, -9 minus, now you subtract the denominator, the exponent, -6. And this is going to be newtons per meter squared. Minus 9 plus 6 is minus 3, right? Minus 9 minus a minus 6 is minus 9 plus 6 is minus 3. So this is 4 times 10 to the minus 3 newtons per meter squared is a Pascal. Now, on an exam, well, this is certainly correct. But 10 to the minus 3, remember what minus 3 is? It's milli. So I would write this, the pressure, as equal to 4 milli, small m, pascals. 4 times 10 to the minus 3 pascals is 4 millipascals. So that would be my answer to this problem. Okay? Well, that should confuse you for a while. So go review that, and we'll continue next time.